Okay. So you see, when we started discussion about strength of materials, at that time we have observed that primarily we are considering strength criteria, right? So what are the strength criteria to be checked? Strength criteria means that whatever is the stresses getting generated inside a structure, that should be less than the permissible stress, permissible or allowable stress. If you remember the allowable stress things and working stress formulations I have discussed, where we have also discussed about factor of safety. So permissible stress in a structure, and the stress whatever is coming in the structure, that should be compared, and the stress in any structure should be less than the permissible stress, right? So permissible stress may be bending stress, it may be shear stress, it may be normal tensile stress, it may be compressive stress, whatever may be the kind of stress. We have understood now by this time that what are the different types of stress. But other than the strength criteria of the structure, you need to check for another one criteria, that is the deflection criteria. Okay? Because whenever there is some load coming onto structure deflects. Okay? Deflect means you have observed that whenever there is a load on a simple supported beam, there is a sagging kind of thing, and sag means bending downward, and bending downward means there is a typical deflected shape coming for the structure, right? So now, because of that load, what is the permissible deflection in the structure? That also needs to be studied. So how do we can define some permissible deflection? If you see different Indian standard codes like Indian Standard Code IS 456 or Indian Standard Code IS 800 for concrete and steel respectively, then you can see that there are different deflection criteria being mentioned over there. Okay? So permissible deflection criteria. But you know the permissible deflection criteria, but how to check how much the deflection of the structure will be? So in today's class, we will start with the discussion on deflection of beams. Okay? So deflection of beams. So now this deflection of beams, there are various methods through which you can calculate the deflection of beams. Okay, various methods. The first method is called double integration method. Double integration method, which is also in a specialized form. This double integration method is also called Macaulay's method. Then you have, I'll come to that, what is double integration method. Then you have moment area method or area moment method. You can say moment area or area moment method. Moment area method for deflection calculation. Then you have Castigliano's method. And also you have the fourth one, that is conjugate beam method. So you have various kinds of deflection calculation methods in your hand, but typically if you see this moment area method, Castigliano's method and conjugate beam method, they will not be discussed in this semester. They are part of your structural analysis course, which is a mandatory course you will be learning in your 5th semester. Okay? So all these methods you will be learning, all the deflection calculation methods you will be learning, because this Castigliano's method and moment area theorem and conjugate beam method, they are very, very important methods where you will be able to apply them in a very effective manner, and also these deflection calculations will be used for finding out the internal reaction and external reaction forces in indeterminate structure. What is an indeterminate structure? Indeterminate structure means the structure which cannot be solved using the simple three equations of statics, like summation of fx equal to 0, summation of fy equal to 0, and summation of mz equal to 0. So if you cannot solve the structure using the simple equation of statics, then you require more equations to solve the structure. And the more equations you will get from a condition called compatibility condition. Okay? And that compatibility condition is nothing but basically it relates somewhere to the deflection of the structure. So if you can relate the deflection of a structure to something, and if you can find out what is the deflection of the structure, then you can also solve the indeterminate structure. So this Castigliano's method, like or momentary or conjugate beam, they are very, very effectively used for finding out the different internal and external forces in indeterminate structure, also through the finding out of the deflections in the structure. Clear? But in this semester, we will be learning about primarily on this double integration method and Macaulay's method. Macaulay's method is a special kind of method which is being derived from the double integration method, and there are some special conditions being applied where you can see the double integration method is changing to Macaulay's method. Okay. Now let us see what is the double integration method. So you have by now learned about the beam bending theory, and from that we have seen that that elastic curve, we have seen that beam is bending downward. Okay, so if there is a bending downward, and we have seen that there is something like here, if I do then I get a row over here. So the curvature of the beam is or curvature of the deflected shape of the beam is 1 by rho. So considering that, if you remember the curvature formula and the elastic and the moment and curvature relationships. So what are the moment curvature relationships? We have derived this in the previous class. M by I equal to sigma by phi equal to E by rho. You remember this? E by rho, right? So this is the equation we have already learned, right? So from there only we will be able to find out how to apply the double integration method for deflection. How it will come? So if you remember from the mathematics, the curvature 1 by rho, curvature of a beam 1 by rho is given by a formula which is nothing but, it is the second integration d2y dx2 by 1 plus dy dx whole square to the power 3 by. This is actually the equation of curvature in terms of y and x, when it is taken in terms of infinitesimal term like dx and dy. Okay? So you must have studied it in your 12th standard or maybe in the first semester course of your engineering. So this is your curvature of any bent up thing, like when there is a bending happening like a circular arc, right? Now you see when the dy dx, we have seen that dy dx term is very small term, right? Dy dx term will be very, very small term. So if dy dx is very, very small, what will happen to dy dx whole square? Dy dx whole square will be much smaller than dy dx, right? And then you are doing it a to the power 3 by 2. So 1 plus that, and then there is a to the power 3 by 2. So if dy dx is very, very small, its whole square will be very small. So what we should do here in our assumption we'll neglect that dy dx whole square term to neglect that dy dx whole square term, or we make it to 0. So if I make this dy dx whole square term negligible, because it is very small, so what will happen to the denominator? Denominator will have 1 to the power 3 by 2. Correct? So what is 1 to the power 3 by 2? 1 to the power 3 by 2 is equal to 1. Right? So if it is that, then my 1 by rho will become equal to e to the power dx. Clear? Is it okay? Now what is 1 by rho? What is 1 by rho? 1 by rho is equal to, if you can see, now 1 by rho is nothing but 1 by rho is nothing but, from this equation if I go, then 1 by rho is equal to m by ei. So 1 by rho is nothing but m upon ei, isn't it? So if I go by from this to this, if I replace 1 by rho, so what I get? We will get d2y dx2 is equal to m upon ei. Got it? Have you understood? So now this m, what is this m? M is moment at any section, right? So you see, m will be a function of x, so mx. You should write like this, okay? Or I can write m is a function of x, something like this. Or you can write m subscript x. So basically, m will be a function of x. What does it mean? M is a function of x. So let's say I have a simple supported beam and I have a point load over here. So if I want to find out bending moment at any section x, if I want to find out what is the bending moment at any section x, the bending moment will come in terms of x. So basically moment will be a function of x, that means the horizontal length of the along the horizontal length. If I take x as a variable, then it will be a function of x. So when m is a function of x, you see d2y dx2, when we are saying d2y dx2, then if I now first integrate it, so why does it double integration method? Why do we call it as double integration method? Now you can see that why it is being called double integration method. So the formulation you have now, d2y dx2 is equal to mx by ei. Now what is this ei term? Ei is a constant term. Ei is a constant term, right? Flexural rigidity. So it is a constant term for a particular section of the beam. So if I take a rectangular beam, I will be constant. For the particular material, U will be constant. So ei is constant. What is varying? Varying thing is your moment. Based on the load, the moments will change, right? So now, if I do the first integration, so after the first integration, what I get? After the first integration, if I do integrate, then I have to do integration in both sides, right? So the first integration of d2y dx2 will become dy upon dx, and here if I do integrate this, so if I do an integration of this, then what I will get? I will get integration mx dx, and 1 by ei obviously will come outside because it is a constant term. So integration 1 by x dx, integration 1 by ei mx dx, or rather I should write it in this way. Ei is constant, so I should bring this ei to this side. So I can write ei dy dx. I can write this ei dy dx, or rather I will write another one step over here to make your confusion clear. I can make this equation something like this: d2y dx2 equal to mx by ei. That means ei d2y dx2 equal to mx, because ei is a constant term. So from this, if I come to this, then ei dy dx is equal to integral mx dx, and obviously I am not doing a definite integral, so I will have what? One constant of integration. So this is what you should remember. This is very important. There will be a constant of integration coming in. So there will be a constant of integration C. Have you understood? Now if I now next do the integration. So the second integration. So basically second integration. Another one time I am doing the integration, right? So if I do integration of dy dx, what I will get? I will get ei into y. So dx will be going on the other side, right? So what I will get? I will get double integral, because one integral already I am having, right? So I will have double integral mx dx, and then there will be another one dx term coming in. Very clearly try to understand. It is double integration, right? Integral mx dx was initial. Now this dx is going on the other side, and there is another one integration coming in. So mx dx, and then another one dx. And then this C1 is a constant term, so there will be integration of C1 also. So C1 will be integrated and it will be written as C1 dx, where I can bring out this C1 on this side. So I can write integral something like this, C1 integral dx, right? Plus there will be another one constant of integration coming. That is. Have you understood? Is it clear? So now you see from the moment equation or the bending stress equation, whatever you say, m by I equal to sigma by y is equal to E by rho, where the curvature of the beam has been defined, and the curvature of beam can be expressed in terms of the differential dy dx. So d2y dx, the second derivative of y with respect to x, d2y dx2 is being termed as 1 by rho, which is the which is basically the curvature, okay? And if I replace that curvature with the moment equation of m by dr, then after two-step integration, that means double integration, what I get the differential. Have you understood? Okay? So this is actually called double integration method. This is actually called double integration method. Clear? Now, the question here is that if I want to find out y, I will be knowing E and I because I know the material properties, so I know E, modulus of elasticity. I know the section, so if I know the section, I know what is the moment of inertia I know what is the moment at a particular section where I am trying to find out the deflection. So if I point out a particular section where I want to find out the deflection, the moment at this section is mx, so this is also known. I do not know what is C1 and what is C2. So how do I find out deflection? So if this equation doesn't help in that case, correct or not? So equation तो ऐसे establish हो गया कि इससे हम deflection नहीं find कर सकते because there are two unknown constants, C1, C2. So from where I will get that C1 and C2? Correct? This is another one very important thing you should understand, that C1 and C2 is to be found out from the boundary condition. Boundary condition means for typical type of support condition, just to initially understand boundary condition. Boundary condition means as a structural engineer or as when you learn about strength of material force, when you learn about bending moment and shear force, at that time you know at what position of the beam what will be the reaction, at what position of the beam what will be the deflection. Okay? So considering that, you can very easily define your boundary condition. So just with example, I will tell you one boundary condition. Let's say I take a simple supported beam. So simple supported beam is like this. So subjected to any load, subjected to any load. So what will be the boundary conditions for simple supported beam? So if I consider my length in this axis, x-axis. So this is my 0 length and this is my L, right? So this point, if I take this as x-axis, so what I can say at x equal to 0, in any simple supported beam, the vertical deflection will be always 0. Isn't it? So deflection angle. If there is no settlement of support, if there is settlement of support, then there is deflection. But if there is no settlement of support, which is the general case we are assuming for now, so if I apply the boundary condition for that simple supported beam, then at x equal to 0, what will be my value of y? Y should be equal to 0. This is what is the boundary condition. Have you understood? And what will be the next? So with one boundary condition, you can get the value of C1. But still you require another one boundary condition because you have two unknowns C1 and C. So to find out the another one unknown C2, you require what? Another one boundary condition. So what will be the next boundary condition? Tell me. What will be the next boundary condition? Well, it's very simple. X equal to. So the next boundary condition will be at x equal to L. At x equal to L again, y should be equal to 0. Have you understood? So two boundary conditions you have. Apply those boundary conditions into this equation. Okay? You will be able to find out two unknowns, C1 and C2. This is how you solve the integral problems, right? Is it clear? Have you understood? If you understood this, then you should be able to solve deflection problems using double integration method. Okay? Now you take the example of cantilever beam. Let's say cantilever beam, if you say. So if I take cantilever beam, so for a cantilever beam, I am erasing this portion. So what is a cantilever beam? The cantilever beam is like this, correct? Let's say I subject it to any load like this, right? So if I consider this as x, so this is my 0, this is my L, correct? Is it clear? Have you understood? So what will be the boundary condition for this cantilever beam? Because you require two boundary conditions, right? So how the deflection will happen? Deflection will be happening something like this, right? It will be happening something like this. So what will be the boundary conditions in this case? So this is a fixed support. So at x equal to 0, what will be the condition? Deflection will be 0. So at x equal to 0, your y is equal to 0. What is the next boundary condition? You can deliver beam. At x equal to L, if you go, then is y equal to 0? No. At the cantilever beam, there will be free length, there will be deflection. So there cannot be any y is equal to 0 over. So there will be some other boundary condition coming, and you should be able to understand that boundary condition. What is the boundary condition? That boundary condition is nothing but, if you observe here, when I draw a reflected shape of a cantilever beam like this, then you can observe at this point there is no angular displacement. Theta is equal to 0. What does it mean? The slope at the point where the fixed support is there, the slope at the point where the fixed support is there, that is what? Slope at that point is nothing but dy dx. So basically again the boundary condition will be at x equal to 0, the dy dx value should be equal to 0. Have you understood? So this is the boundary condition for cantilever. Any confusion on this? Have you understood the second boundary condition? What I have told? Is it clear? In a cantilever beam where it is fixed like this and then it is bending like this, then what is happening? No displacement over here, and there is no angular displacement also at the fixed support. So there is no angular displacement means theta is equal to 0. So if theta is equal to 0 means theta is what? Theta is nothing but equal to tan theta. And what is tan theta? Tan theta is nothing but dy dx. When theta value is very small, then tan theta is equal to theta is equal to dy and dy by dx, right? That's what we have understood earlier also. So dy dx should be equal to 0 at what? At x equal to 0. So this is the boundary condition for cantilever. Have you understood? Clear? So now let's move to some condition like let's try to solve one problem. Then your idea will be clear on this. Okay. So let's take one problem and try to solve and find out the deflection using double integration method. Okay. So let's take a cantilever beam. Let's say this is the cantilever beam, and let's say very simple problem. Let's try to find out if this beam is subjected to a load B over here. So at the free end, a load B is being acted on a cantilever beam, and the length of the beam is, let's say, L. Correct? Length of the beam is L. Correct? So now you see there will be two different cases of bending moments. One is sagging, one is hogging, right? So depending on the hog and sag, you can take the value of your moment. So in case of a cantilever moment, what do you do? Generally we term it as a negative bending, right? So negative bending moment, minus L, right? So now what is my equation for solving using double integration method? So EI V2I dx2 is equal to what? Mx or Mx, something like this, right? Correct? Now if I take any section, let's say if I take, so I am considering my x in this direction, right? I am considering x in this direction. Correct? So if I take, let's say, any section at a distance x from here. I take any section x from here. Correct? Is it clear? Now, what will be my bending moment at this point? So at the section, at a point where I am taking the section, I have to find out what is the bending moment over here. Right? And it should be coming in terms of x. It cannot be, it may be a fixed value also. But if it is a fixed value, then only it will be dx will be there, m dx will come, right? But here it will be terms of what? It will be terms of x. So what will be the bending moment at this section? So if I this length is x, so what is this much length? This is actually L minus x. Correct? So the bending moment here, simply if you see, it is P into L minus x, and it will be negative bending moment. How much will be the bending moment? P into L minus x, right? And it will be negative bending moment. So if it is negative bending moment, then you see ER, what I can write, ER D2R dx2 is equal to minus of P into L minus x. Can I write this? Simple, very simple. Okay? Now you try to solve yourself. So what will be my what is called? So if I take this minus on this side, I can write minus EI d2i dx2 is equal to P into L minus x. Because I will be doing integration on the other side, let's keep this minus on the other side. Okay? So if I do the first integration, what will come? Tell me, what will come? First integration. So if you see, very simple way, if I try to do it, then it is nothing but PL minus PX. This PL minus PX. And P is fixed value. P is fixed value. So P needs not to be integrated, means it is a constant value. So now, if I try to integrate, so it will become EI, first integration if I do, EI dy dx should be equal to what? Equal to, what will become? Integration PL dx, right? Integration PL dx. So, I'll write the step, then it will clear PL dx minus, what will become? Integration px dx. Correct? आएगा कि नहीं आएगा? plus what will come? Now integrate. So you will get it. So what will be the integration value? So it will become minus EI dy dx. Everyone can understand? So now this is equal to what? PLX minus what will become that? X dx का इंटीग्रेशन क्या है? x square by 2 dx square by 2 integrated plus. Everyone understand? Is it clear? So I have done the first integration. Is it clear? कोई डाउट है अभी तक? Okay? Now what I have to do? So one way of doing it, you first try to put the boundary condition and proceed. But it is better practice you do the double integration and then at the end you put the boundary condition and find out the value of C1 and C. Okay? Now if I integrate for the next time, what will become? So if I integrate for the next time, then I am using it. Okay? So if I integrate for the next time, so I am bringing this to here. Okay? So if I integrate next time, what will become? So minus EI divide dx will be going to the other side. So it will become EIY is equal to integration PLX. Then there will be a dx. So you see, we have put a double integral sign. You remember? While formulating, we have put a double integral sign. So what is this double integral? You understood? So one step by step you are going and integrating. Okay? Don't worry about the double integral sign. Okay? Hello, sir. Please understand. Right? Listen. Okay? So PLX dx minus integration px square by 2 dx plus what will become in this one? C1 will come out here, C1 dx plus, isn't it? Please do step by step, don't jump the step, because if you jump the step, then there is every chance that you will make some mistake. Okay? So now if I go for the next step, then what will become this one? What will be the next one? Next step, simple EI, Y, and integrate. So tell me, PLX, what will become? PL x square by 2 minus what will become this one? P x square का integration क्या है? X cubed by 3. So 3 into 2, denominator there is a 2, 3 into 2 6. So minus P x cubed by 6 will come plus C1x plus is it clear? Have you understood? Any question, any doubt at this point? No? So now you put the condition for boundary. So what is the condition for boundary? So what is the being we are considering? We are taking cantilever beam. So what will be the cantilever beam boundary condition? Just now we have understood. At x equal to 0, it will be y equal to 0. And at x equal to 0, dy dx will be equal to 0. Clear? Dy dx will be equal to 0. So you put the boundary condition at x equal to 0. At x equal to 0, what is the boundary condition? Y equal to 0. So if I put at x equal to 0, so putting the condition in this equation, if I put the condition back in this equation, final equation, okay? So what will happen? This will become EI minus EI into Y will be becoming equal to 0. What will be this? 0. X equal to 0. So B x square 0. This will become 0. This will become 0. So what will be my value of C2? It will become equal to 0. Have you understood? Here? So C2 is becoming equal to 0. What I have done? Only I have put back the boundary condition of at x equal to 0, because it is a fixed support at the position at x equal to 0, the deflection value y will be equal to 0. Clear? Now next, condition is what? For a cantilever beam, what we have understood? At x equal to 0, we have understood at x equal to 0, what is dy dx equal to 0? So where is the dy dx equation? So dy dx equation you see, dy dx equation is here. Correct or not? dy dx equation is here. So at x equal to 0, dy dx equal to 0. So if I put dy dx equal to 0, so this becomes equal to 0. What will happen to this? 0. This will become equal to 0. So C1 will be becoming, so this will give you C1 equal to 0. But you see, it is coming because it is a cantilever being C1 and C2 becoming 0. But you will have to go with pointing out towards the boundary condition. Without putting boundary condition, you cannot say whether your integration constants will be becoming 0 or not. That is very important. And always you will not get equal to 0. You will see different problems where you will not find that C1 and C2s are becoming equal to 0. Is it clear? So now considering that, what you get? Finally what you get? Look. So final equation after putting the boundary condition, if I say, then finally if you get that equation, so I am placing this. So what we have got? We have got the value of C1 equal to 0. We have got the value of C2 equal to 0. So putting the boundary condition, C1 becomes equal to 0. C2 becomes equal to 0. So basically, finally the equation becomes PIY is equal to PLX squared upon 2 minus EX cubed by 6. Is it clear? Have you understood? So this is the equation of deflection. This is the equation of deflection for a cantilever beam subjected to a point load P at the end, at the free end. Okay. Now, if I want to find out deflection at any point in this beam, so at x equal to 0, you put it. At x equal to 0, what will be deflection? At x equal to 0, if I put x equal to 0, deflection y will be equal to 0. Suppose I want to find out deflection at the middle of the beam because of the point load. How do I find out? I will put at x equal to L by 3. So if I want to find out what is the deflection at this point, at the middle of the beam, it will be x equal to L by 3. If I want to find out at length, let's say point L, so what will be my deflection? I will put x equal to 0.1. If I want to find out what is the deflection at the free end means where? Free end is where? X equal to L. So if I want to find out deflection, at free end, so free end में deflection कितना होगा? X equal to L, at x equal to L, right? So if I put at x equal to L, please find out dy y is equal to, how much will be? I put x equal to L, so PL by 2 minus PL by 6. Find out how much will be this coming. Find out. By 6, find out minus PL by 3. So it will become minus PL by 3. आएगा कि नहीं आएगा? Because you see, there is a minus sign over here. It will come PL cube by 3. So EI into Y will become minus PL cube by 3. Correct? I should not write this way. I should write this equal to minus to PL cube by 3. And then if I change this minus sign over there, so what will be my Y? Y will become minus PL cube by 3. What does this minus sign indicate? Minus sign indicates that deflection is downward. So जो लोग डिप्लोमा से आए हैं वो लोग ये सीख के आए होंगे that deflection at the free end of the cantilever is PL cube by 3. Now have you understood how it comes? It comes through double integration method in this. So you need not to remember any beam, any kind of beam you can find out this way. The deflection is the double integration method. But one point you should understand here that very important point is understanding the boundary condition, because boundary conditions are very, very important. Okay? So I think let us conclude our class